The second place where it messes up is windowing, okay? And so what windowing does is it adds this little wiggle on the spectrum that we're going to sample. And really that wiggle stays with us through the whole process. There's the wiggle, and then we get the heights, okay? And when we get the heights, we're actually getting the heights of that wiggled signal, and that's exactly right? We're getting the Fourier transform of that wiggled signal, but there's some wiggling that has been added because of the windowing function. So that wiggle, where does that come from? It's because I take my sampled signal, I multiply it with a rectangular window in this case, which corresponds to convolution in the frequency domain, and I'm convolving with the sinc function, and that adds that wiggle. This is really an extreme case where we can really see the effect of what windowing does to the situation. So here we've got a sine wave, okay? This is kind of just thinking about it without any sampling. We're just doing the windowing and looking at what happens. So if we have this sine wave and we window it, then we multiply it in the time domain with this rectangular function, and that just gives us the windowed sine wave. What that would do in the frequency domain is you're convolving with a sinc. The sinc has zeros at 1 over the width, 2 over the width, 3 over the width, okay? And when you then have these impulses and you convolve with a sinc, then you end up with the sinc function there, okay? And now if we calculate the DFT, what we're actually going to do is we're going to basically get samples for this thing in the frequency domain. That's what the DFT is going to give us, not samples for this thing. So we see these little blobs coming out. So windowing, bad, not good. Okay, what can we do? The one thing we can do is we can make the width here very, very big. Okay, you can't always do this. We live in a broken world, so there's some limit to how wide you can record your signal, like like what the width is here. But if we make this very wide, what would happen to the sinc function here? Just show with your hands. It will get squashed, okay? And that's very nice, because the closer this thing is to an impulse, if we can get this as close as possible to an impulse, then we're just convolving with the impulse here, and then we will end up with perfect impulses here. And then the DFT would actually sample that spectrum. Okay, but we live in a broken world, so we can't sample with a very, very big window. So what can we do? Okay, wonderful. That's exactly right. So what you can do is, instead of taking a rectangular window, we can play around with the shape of the window here. We can do weird and wonderful things, like maybe not, like these sharp edges are pretty extreme. Maybe that's messing up things, okay? And you're right, so people that were very clever with different names, someone's name was Hamming. Hamming was actually like really super clever. He came up with a ton of stuff. I don't know if he came up with this window or whether he's just like, they just named the window after him. People have played around with different window shapes. And so we get the one that we've been using up to this point, which is this rectangular window. You can use a Hamming window, which is some function. Again, you just ask NumPy or SciPy, give me the Hamming window, and then it gives you basically the shape of that window. Another one is the Blackman window that looks like this. These things look pretty extreme, and now we need to understand what are they actually doing. Okay, and to see what they're doing, you need to look at basically the Fourier transform of these windows and see what do we get for using a kind of a weird window like the Hamming window here. And so at the bottom of this plot is the Fourier transform of those three windows. And just stare at this for a second. So they're all W wide. Okay, so they start at minus W over 2 and they end at W over 2. The rectangular window spectrum goes like this and then has these side lobes. The Hamming is somewhere here. There's also side lobes. And then the Blackman is also here. It also has side lobes. Its side lobes actually gets very small, so you need to really zoom in order to see the Blackman window's side lobes. Stare at that for a second and tell me, what is the trade-off between these different window types? That's exactly right. So they're wider. Then, like the Hamming window is wider, the Hamming window here is wider than the rectangular window. That makes me happy or sad? Sad. because I want something that's sharp. But I get something in return for that. What I get is very tiny side lobes compared to the monstrosity that is the side lobes of the rectangular window. Okay, and the Blackman window is even more extreme. It gives you a very, very wide signal, but then the side lobes are so small that you have to zoom in. I mean, this thing doesn't even show the rectangular window side lobes here. I don't know, it's like whoop, something like that. Okay, so the Blackman is even better. And so you have this trade-off. You have a decision to make. And the cool thing is, if you know that you can take a really long window, then it makes sense to use one of these other window functions, because with a very long window, these things are going to get sharp anyway. And then I get rid of my side lobes, and that makes me happy on the inside. Okay.